In this lecture for Chapter 3 for Statistics 252, I'll discuss using frequency to calculate the mean and also start the work for calculating standard deviation, variance and standard deviation. In this problem, in the actual homework, of course, you have a lot more ages, but here we just have a few just to demonstrate what's going on. We have a lot of data. Okay, if you want to calculate the mean of this data, it's quite easy because you only have a few numbers. You could just add these up and divide by however many you have. 10. Okay, easy enough. But if you have quite a few of them, which you will in the homework, it's easier to organize them. You can just organize them right here. We've got a 23, and instead of writing another 23 like you did to calculate the mean before, you could just write them in order. So it'd be 23, 24, 25. Looks like we've got a 28, 29, and a 30. That's what's shown up here. And then put some tally marks for how many you have. In this case, of course, it's trivial to do it in this example. You have 2 of these, so you have a frequency of 2. The 24, there's only 1. 25, I think the only one that was, and 2 of these, and 1 for the 30. Okay, so here's your frequency down in this column, and here are the ages up here. Like I say, it's trivial in this case, but if you have more numbers, this works out too. So you calculate, to calculate the mean, you take a sum of the frequency times the data value, and you divide by the sum of all the frequencies. In other words, you add up all these numbers down here in the frequency column, and you should get, how many do we have up there? 10, I thought. Like 8. Well, it helps if you put all the numbers down. And it looks like I forgot the 26, so there would have been a 26 in here. Alright, so you take and you add up all these frequencies, which should equal the number of the values that you started with in the first place, in this case 10. Then you take each value and you multiply by the frequency. So the first is be 23 times 2. Then you would have 24 times 1, and you keep working up through all those and divide by the 10, and that will give you your mean, your arithmetic average. The mean is the arithmetic average. And now these are lined up, but you would have to look at the frequency and find the middle of the frequency. In this case, we've got 10. It's an even number, so we'll be averaging the 2 middle numbers. We can do that by just looking at the frequency. 1, 2, 3, 4. Okay, it's going to be these 2 numbers that get averaged, the 26 and the 28. So it would be 27 would be the mean. And for modes, you can pick the modes out right away. Here's mode is 23, and another mode is 29. Remember, you can have more than one mode, but only one median and only one mean. And now we'll start calculating standard deviations and variance. So far we just calculated mean, median, and mode, which were the measures of central tendency. They were your averages. 3 different averages, and of course the weighted mean too. Right, now we're going to look at standard deviation and variance, and those are measures of how much the data is dispersed, or on the other hand, how much the data is clumped together. Small values of standard deviation mean that the data is centered on the mean. Large values of standard deviation means the data is spread out far from the mean. So to calculate this, you need the mean. So the first thing you have to do is calculate that from this truncated data set here. So the first thing to do is calculate the mean for both of these. You're going to compare 2 stocks. So you calculate the mean here, and you calculate the mean over here. And that's easy enough. In this case, you just add up these x's, add all the x's, and divide by however many there are, in this case 7. So when I added up and divided, I got 3.57 over here, and on the other one I got 5.14. I'm just going to work on this, on the Vanguard stock index right now. So here's your mean. We'll just say it's approximately 3.6. Now you look at each data value and you find out how far it is from the mean. So I take each one of these and I subtract subtract 3.6. That's what it says to do right here. So when I do that, I get this column. I already did this, so I'll write these numbers down for you. Minus 3.6. Remember, 0 is a perfectly good value, not just something to be ignored. 17.4. Okay, minus 11. I got a minus 14.6. This is how far all that data is, and you'll notice this has your negative numbers as well as positive numbers. But you actually don't care. You just want to know how the data is clumped. So the next thing you do, you're now calculating your variance, is to take that data, take those numbers, x minus mu, and square them. So after I square them, I get okay, so now I've done the second column. You'd have, of course, do the same thing over here. And here would be the mean that you would use in this case. And now you add up all these that are all the squareds, the third column, and that's what's given here to calculate the mean. I'm sorry, to calculate the variance. And that is... okay. I just erased some of that to give some room. So the sum here was... okay, that was the sum. I remember all these columns have been filled out before. Now to find the variance, which will be sigma squared, you take the 2451.72 and you divide by the number of data points you have, in this case 7. It'll be different on homework. And then you get something like 350. And that's the variance. The standard deviation would be the square root of that. So you just take its square root of the 350 and get something like 18.7. That's the standard deviation for this data set. You find the same for the other data set too, so you can compare them. Now, in order to compare them, it doesn't make a lot of sense because the means are different to just look at the standard deviation. So you compute what's called the coefficient of variance, and you take the standard deviation for each one and you divide by the particular mean that you have. In this case, the mean was 3.6 here for this case, and over here the mean was 5.61 or something like that, 5.14. So I would take this for the coefficient of variance and I would divide by the 18.7. And this, of course, is how it looks on homework. First you compute the mean for the total stock index, then you compute the mean for the balanced index, and there'll be more numbers than I showed here. Then you fill in those remaining columns, finding how far each data value is from the particular mean for the data set that you're working with. Square them and add them up to get the variance after you divide by the number that you have. Take the square root, and then you have the standard deviation for both of them. Then you want to compare them. So then to compare them, you compute that coefficient of variation for each fund. That means you take the standard deviation and divide by the mean. I've included some terms here because just to show you that these means, standard deviations, and the coefficient of variation are not just idle exercises in a class, are actually used. Here's some terminology for stocks. The mean is called the expected return. That's the average you're going to get. That's what you expect. Well, I'll probably get something. That'll be my expected return. The standard deviation is called the risk. If you have values that are spread out very far from the mean, that's sort of risky. In fact, you might lose everything, or on the other hand, you stand to have a large gain. So standard deviation is the risk. That ratio, that coefficient of variation, which is right here, taking the standard deviation and dividing by the mean, is called the risk per unit of expected return. And that gives you a way to compare different stocks, because they'll have different averages and different standard deviations. Looking at the standard deviation alone is not a good comparison. When you look at those standard deviations and means just as numbers on the page, they're interesting, perhaps slightly interesting, but they make a lot more sense when the data is graphed. So this is a typical graph of the data showing the frequency versus the data values. And this is your standard bell-shaped curve, or Gaussian distribution, or normal distribution. Alright, here's the mean with the symbol mu. And again, you would use x bar if it's a sample and mu if it's a population. But I'm using the Greek letters a lot because I know people need to get used to them. So this is your Greek letter mu, lowercase, and in this bell-shaped curve, it's right in the middle. Also, because it's symmetric, the median is also right in the middle as well, but we don't worry about that right now. The mean, here's the mean for the standard deviation, it's right in the middle. And now these lines mean moving a certain number of standard deviations away. Okay, so if I take the mean and I add the standard deviation to it, I would get this line right here. That's the mean plus 1 standard deviation. And this is the mean minus 1 standard deviation. And now we could move over here to this line, which would be the mean plus 2 standard deviations. And this would be the mean, minus 2 standard deviations, and then I put the 1 for 3 out here also. These are very handy numbers to have on here, because for the bell-shaped curve, the numbers, the number of data values in each region is well known, and I ask you to mark that on there. It's symmetric, of course. There's about 34% of all the data values occur right about in here, between the mean and minus 1 standard deviation, and also this way. So between here and here, you get 68% of all your data values. When you move out to 2 standard deviations away, you get 95% of the standard deviations. 90% of all values lie within 2 standard deviations. And if you're out here, it's 99.7%. It's about 14% here, about 14% here, about 2 1/4 over in here of the data values. But when you add all these up, that's your distribution between plus or minus 1 standard deviation, or the way it's set, it's within 1 standard deviation. That means plus and minus as well. Within 1 standard deviation, 68% of the values, so right in there. 95% of the values lie within 2 standard deviations of the mean, and 99.7 lie within 3 standard deviations of the mean. You might have seen or gotten some spam email about 6 sigma. That's what they're talking about. You want to be, if you're up here, you can imagine how few values are way up here, 6 standard deviations away from the mean. Some quality control cases, things that have to be, are very dangerous. You want the chance for failures to be several standard deviations away from the mean. And 6 sigma means outstanding performance. I think they're using that to denote how to get very wealthy and be up there in the 6 sigma away from the average salary.